All right, our next topic, we need to end up going a little bit to the side on this since we didn't talk about how to do this earlier. In order to end up understanding how to find what torque is, we have to end up introducing the concept of a cross product. So, in order to get a cross product, it's a way you combine two vectors. The order matters, unlike the case of a dot product, but it's a way of combining two vectors where we get a third vector out. The third vector is always perpendicular to both of the individual vectors, so you can't do all of it in 2 dimensions. So you have to deal with this in 3D. And I will be looking at trying to illustrate this myself with my left hand because the camera reverses it, and I'm going to see whether I can end up making this so that you can understand what's going on. Even though we're going to use a right hand rule, it's just if you're wanting to follow this because the camera reverses it, that's what we get. So the magnitude, remember it's a vector, so it has a magnitude and a direction. The magnitude of a cross product is the product of the magnitudes of the individual vectors times the sine of the angle between. So remember, for a dot product, product of magnitudes times a cosine. The other thing is a dot product is a scalar. It's a number. So when we calculated work before, work's a number. It's not there's no direction or anything like that. It's just a plain number. So a cross product, though, is a vector quantity, but its length, the magnitude, is equal to that. What does a cross product mean? If you want to end up thinking about, if you have two vectors that start at the same point, you could end up forming a parallelogram from those, and we did that sort of thing before in lab, where you were finding geometric sum, where you took the sum of this vector plus the sum of the other one, and that's the same as adding the two the other way around. So if you're wanting to figure out what the area of that parallelogram is, the area of the parallelogram is actually the magnitude of the cross product between those two vectors. So again, it's the fact that the cross product comes up is not as obvious, but nevertheless, that is the way it works. So in order to find the direction of your cross product, what you need to do is to align your right hand such that from your wrist to your fingers points in the direction of the first of the two vectors. So if I want to end up having a vector that's going to the right, so it'll look like this. So I have a vector going to the right, and then I want to cross it with a vector going this way. Bring my finger so you can see. So I want to cross it this way. Then I'll end up taking this and cross in that direction, close my fist, and my thumb points in the direction of that cross product. So in this situation, if you have to the right, and then crossed that way, you end up getting a cross product that goes upward in the plane of your device, whatever it is that you're using to watch this. Again, it's a little unwieldy for me to do it because if this was live, and I'd be using my right hand because I'd illustrate it as being my right hand rule, but in the camera, this will end up working. Again, it feels very strange, but we're trying to deal with it. But again, it's your thumb will point in the direction of your cross product after you evaluate it, doing it that way. So I gave an illustration. I have vector A and vector B. I already moved it so that their tails are touching, so that way it's easier to read what the angle is. But in general, of course, the two vectors don't have to be touching, just like with a dot product. Whenever we talked about the angle there, again, we thought about, okay, I'm going to slide the vectors until their tails touch so that it's clear what the angle means. If I have them somewhere out over here, then what the angle is between this and that is not necessarily clear. I move them so their tails are touching, then the angle makes more sense. So it's more obvious what we mean. So in any case, if we have that vector A crossed with vector B, then to find the direction of the cross product, we'll take the direction of A and we'll cross it toward B. And in that situation, the cross product is going to end up pointing into the plane. So if I have, let me see if I can make this work. So this will be the direction of A. Then the direction of B is this way. So I want to curl these fingers toward that direction. So I curl them like this, right? Curl them that way, close my fist. So then my thumb is going to be pointing into the direction into the screen. You should also check. So if you have B cross A, then in that situation you've got B that is going this way. You want to cross to A, which is going in that direction. So you cross your fingers up toward where this one is. You cross those together, and your thumb then is going to point in. So this cross that way will end up going. Will end up coming. This. I'm really not used to doing this with my left hand. This crossed that way will give you a thumb that points well. You check it yourself. Sorry, I'm having difficulty using my left hand. One thing though that is useful to use with finding cross product magnitude. The illustration I gave was I had a vector A which is pointing that way, and then a vector B which would be pointing like this. So the angle between these two, the sine of that angle, the sine of this angle over here, they're exactly the same. So the sine of an angle is equal to the sine of its supplement, excuse me. So because that's true, it doesn't matter which one of those we end up using practically to end up finding my the value of the cross product. And the next thing we're going to look at is then starting to talk about torque, which will end up then leading into being able to do rotational dynamics calculation.